Okay, so let's go ahead and do this example 8.5.1, and we are essentially trying to solve this initial value problem. The forcing term is a piecewise defined function. Okay, just as a note, I am following the steps outlined in the slides that are posted on Slack, and these are the same steps as the steps that are in the textbook. So on page 432, you can find the same steps that I'm following. Okay, so let's go ahead and let's carry out step number 1, which is to find the solution to the initial value problem. So let's do step 1, which is going to be to solve the IVP, not the IVP, but to solve the homogeneous. No, sorry, I'm getting confused here. Okay, so first let me do this. Let me just to kind of clear things up. 1 is going to be f sub 0 of t, and -1 is going to be f sub 1 of t. Okay, so I've got my functions f0 and f1. Step 1 is to solve y double prime plus y equals f0, which is 1, equals 1. Y of 0 equals, what is it? Y of 0 equals 2, and y prime of 0 equals -1. Okay? And again, I'm following the steps that are outlined in the slides. So basically, I need to solve this equation right here. Y double prime plus y equals 1. Y of 0 equals 2. Y prime equals -1. The fastest way to do that is to use Laplace transforms. So I'm going to solve this using Laplace transforms. You could solve it several different ways because we know several different ways. You could use variation of parameters, right? We didn't talk about the method of undetermined coefficients, but if that's something that you're familiar with and you'd like to use that, go for it. I'm going to use Laplace transforms. Okay, so now with the Laplace transform, I'm going to take the Laplace transform of the left-hand side, y double prime plus y, and that's going to equal the Laplace transform of the right-hand side, 1. Now, I'm going to use linearity to say I've got the Laplace transform of y double prime plus the Laplace transform of y, and that is going to equal the Laplace transform of 1. Now, by now we've done so many examples, we've done this several times, so you could either look it up or you could already know that the Laplace transform of 1 is going to equal 1 over s. Okay? The Laplace transform of y, we're going to denote it by capital Y of s. And we use the theorem, I think it is theorem 8.3.2. Let's see, it is theorem 8.3.2 that tells us that the Laplace transform of y double prime is going to be s squared times y of s minus y prime of 0 minus s times y of 0. Okay, so I've got these facts over here, and I'm going to substitute each of these facts into my equation on the left. Okay, so the Laplace transform of y double prime is going to be s squared times capital Y of s. Now remember, y of s is a Laplace transform of y, minus y prime of 0 minus s times y of 0. The Laplace of y, I'm denoting just by big Y of s, and then the Laplace transform of 1 is just going to be 1 over s. Okay, now I can simplify this more because I know y prime of 0 is supposed to be -1. Okay, so this y prime of 0 is -1, and y of 0 is 2, so minus s times 2. And then I've got s squared y of s. Okay, so now I'm going to put it all together, and I will get this plus this equals this. So let's go ahead and write that out. So I will have s squared y of s plus 1 minus 2s plus y of s equals 1 over s. I am going to try to solve for y, big Y of s. So I'm going to add 2s to both sides and subtract 1 minus 1 plus 2s. So on the left-hand side, I will now have s squared big Y of s plus big Y of s equals 1 over s minus 1 plus 2s. Now I'm going to factor out, because remember my goal is to get y of s by itself. So I'm going to factor out y of s times s squared plus 1, because that's the same as just 1, right? So I'm factoring out y of s on the left-hand side. And on the right-hand side, I've got 1 over s minus 1 plus 2s. Now I have y of s equals, I'm just going to divide both sides by s squared plus 1. So I have 1 over s minus 1 plus 2s, all divided by s squared plus 1. Okay, now the next step is to take the inverse Laplace, and that will give me my solution for y. Because look, so watch this. If the Laplace of y is supposed to solve my differential equation. Little y is a solution to my differential equation. So if the Laplace of little y is big Y, then the inverse Laplace of big Y is little y. Okay, does that make sense? So if the Laplace of little y is big Y, then do the inverse Laplace. The inverse Laplace, right? Take the inverse Laplace of both sides. Now, what's the inverse Laplace of the Laplace? That's just y. So y is the inverse Laplace of my big Y. This was my solution to my differential equation. Okay, so that's why when we get to this step here, big Y of s, the next thing to do is to take the inverse Laplace of both sides. So I need the inverse Laplace of 1 over s minus 1 plus 2s over s squared plus 1. Now you can do that however you like. On the left-hand side here, this is going to be equal to little y. But I prefer to use, I'm going to use Mathematica. So let's see here. So I'm going to type in, so into my Mathematica, I will type just inverse Laplace transform. So let me do that right quick. The reason why I'm not doing it on the iPad is because, you know, I don't know how to use my iPad with Mathematica. Probably there's an app that I need and I don't have it. So let's see here. So I'm just going to type in inverse Laplace. Okay, I misspelled it. Inverse Laplace transform. Okay, bam. Here we go. Now in it, I'm going to put 1 over s. So everything is going to be in parentheses 1 over s minus 1 plus 2s. Okay, and I'm going to put parentheses all around my numerator. Then divided by, and then in my denominator, s squared plus 1. Okay, then comma, I need s comma t, shift enter. Okay, and I got that y is equal to 1 plus cosine of t minus sine of t. Okay, so I've completed step 1, which is to find the solution to this differential, right? Solve this differential equation. Okay, I did it. My solution is 1 plus cosine t minus sine t. Now I'm ready to do step 2, which is, let's see here, compute. So let's see here. Step 2 is, okay, so for step 1, the conclusion is y of t equals 1 plus cosine t minus sine t. Okay, so that's step 1. Now step 2 is to compute C naught, which is y naught of t1, and C1, which is y naught prime of t1. Okay, sorry, y naught is supposed to be the solution that you find in step 1. Now, what is t1? T1 is the point where you have your break. So for us, t1 is going to be pi over 2. Okay, so t1 is going to equal pi over 2. And I need t1 is pi over 2. So I need y naught of pi over 2. And I also need y naught prime of pi over 2. Okay, y naught of pi over 2, that's going to be easy. That is just 1 plus cosine pi over 2 minus sine of pi over 2, right? Because I've got my y naught right here. And cosine of pi over 2 is going to be 0. Sine of pi over 2 is going to be 1. So I have, actually, this is equal to 0. Now, what about y prime of pi over 2? I can go right here and y naught prime of t, I need a formula for it. Derivative of 1 is 0. The derivative of cosine is negative sine t. And the derivative of sine is cosine t. Okay. So what is y naught prime of pi over 2? It is going to be negative sine pi over 2 minus cosine pi over 2. Now, this is going to equal negative 1 minus 0, so I just get negative 1. So C naught is 0, C1 is negative 1. So that is the bottom of step 2. C naught equals 0, C1 is equal to negative 1. Let's move on to step 3, which is to find the solution of what does the solution need to be? The solution needs to be of y double prime plus y equals negative 1. Y double prime plus y equals negative 1. And I need y of t1. What is my t1? T1 is pi over 2. So y of pi over 2 equals 0. Y prime of pi over 2 equals negative 1. Okay. How am I going to do it? I'm going to do it essentially the same way that I did before, which is I'm going to use Laplace transforms. So the Laplace transform of y double prime plus y is equal to the Laplace transform of negative 1. So on the left-hand side, I will have s squared times y of s let's see here. What are my formulas? Yeah, minus y prime minus sy of 0. So minus little y prime of 0 plus plus um, plus plus, let's see here, what is it? It is, oh, sorry, minus sy of 0. So let me erase this. Minus s times y of 0 plus, no, what is the, hold on, let me just erase this because it is not seeming right, doesn't feel right. The reason why it doesn't feel right is because I don't know y of 0 and y prime. I've got values at pi over 2. So let me look back at my, and I got to make sure I've got my formula correct. This is the theorem 8.3.2 is what I'm looking at. 8.3.2. Theorem 8.3.2 gives it only at, yeah, f of 0. So let me see. So it could be, I don't want to do another. You know what? Here, let's do this. Let's do this. Let me actually pause right here.